Hello, this is the extension of time response of second order system model. So in the previous class we have seen how the when the zeta changes and how the poles are changing, nature of poles are changing and the response is changing, output is changing. Today we will see the very special case that is called find the time response of second order system under unit step input for underdamping. It's a very special case, important case, because 90% of the systems are underdamping. Okay, so solution. In the second order means we know the transfer function of second order system, that is what? Standard form of second order system, C of s divided by R of s equal to omega n square divided by s square plus 2 zeta omega ns plus omega n square. Second order, standard form of second order closed loop transfer function. And in the question, you read the question, unit step input. Unit step input means R of s equal to what? 1 by s. This is called what? Unit step input. Correct. Then for underdamping means what? When the zeta is greater than 0 and less than 1, it is called underdamping. So I have to consider unit step, I have to consider underdamping. For a second order system, what I supposed to find? I supposed to find C of t, time response of second order system, C of t. Now I will substitute this R of s equal to 1 by s in the above transfer function. Next, C of s equal to omega n square. Okay. How to find C of t from C of s? By taking inverse Laplace. But to take an inverse Laplace, to convert multiplication factor into what? Addition factor. For that, there is a need of partial fraction. You know there are three formulas of partial fraction, three forms. Suppose x plus 2, x plus 3. The highest power of x is 3, so that you will get ABC constant. And you find ABC constants. Suppose second form is like x square plus x plus 3. So once again three constants are required. Why? Because the highest power of x is 3. And the third one is this third form. Once again three constants are required, but here this is third form. So this problem or this equation comes under the third form of partial fraction. Here also the highest power of 3, so ABC is required. So now I'll write in this fashion: omega n square divided by s into bracket s square plus 2 zeta omega ns plus omega n square is equal to what I supposed to write? A by s plus bs plus c divided by s square plus 2 zeta omega ns plus omega n square. This third form of partial fraction. Third form of partial fraction. Now you take a LCM. Here this side is omega n square and divided by S into bracket S square plus 2 zeta omega ns plus omega n square, and this side is LCM 2 zeta omega ns plus omega n square. So this side S square plus 2 zeta omega ns plus omega n square, and above this is S. So I'll write A into this, A into S square plus 2 zeta omega ns plus omega n square plus S into bracket B SC plus C get cancelled. So omega n square is equal to A S square plus 2 zeta omega n S A plus A omega n square plus B S square plus C S. Now what I will do, I will take S square is a common, S square A plus B, otherwise I will write like this, A plus B S square. Then I will take a S coefficient 2 zeta omega A plus C, then the remaining constant. This side no S squares, I can write 0 S square, no S I can write 0 S, and constant is omega n square. Now you have to compare the coefficient. You start from constant, so omega n square is equal to what I'll write? Omega n square is equal to A omega n square. So omega n square get cancelled, we get A equal to 1. Then I'll compare S coefficient 2 zeta omega Na plus C equal to 0, and A equal to what? 1 plus C. So C is equal to minus 2 zeta omega n. Next, A plus B is equal to 0, then A is equal to 1, then B equal to what? Minus 1. Now I get ABC value. A is equal to 1, B equal to minus 1, C is equal to minus 2 zeta omega n by using comparing coefficient. Now I will substitute ABC value in the above equation. That's what? Omega n square divided by C of S equal to A by S. So now A by S, A is equal to 1, A by S plus B by B S plus B plus CS, BS plus C, B is minus 1, BS in plus C means what? Minus 2 zeta omega n divided by S square plus 2 zeta omega ns plus omega n square. Now I'll write C of S equal to 1 by S minus S plus 2 zeta omega n divided by S square plus 2 zeta omega ns plus omega n square. Okay. Now, may I take a inverse Laplace, but you have to see the standard form of Laplace transformation. For example, Laplace of e raised to minus et sine of omega t equal to s plus a whole square plus omega square, and numerator is omega. Otherwise, Laplace inverse of omega divided by s plus a whole square plus omega square equal to e raised to minus at sine of omega t. Otherwise, a Laplace of e raised to minus at cos of omega t equal to s plus a divided by s plus a whole square plus omega square. If I take Laplace inverse of s plus a divided by s plus a whole square plus omega square is equal to what? E raised to minus at cos of omega t. I need these two formulas. But here I need s plus a perfect square. How to make it a perfect square? Here I need a perfect square. So we know that how to make the perfect square. How to make the perfect square? S square plus 2 zeta omega ns plus I will take a half of s coefficient. If I divide it by 2, then zeta omega n. Half of s coefficient square, adding as well as subtracting. Adding as well as subtracting. Now I can rub this as well as I can rub this also. So I added half of s coefficient. This becomes what? S plus zeta omega n whole square minus zeta omega n whole square. Okay, s square plus 2 zeta omega ns plus omega n square plus there is a omega n square. You are added, the last term is plus omega n square. So now I'll write plus omega n square minus zeta square omega n square. Now s plus zeta omega n whole square is equal to omega n square into bracket 1 minus zeta square. What is this omega n square? Omega n square plus omega n square, that is omega d square. I'll write omega d equal to omega n root of 1 minus zeta square, damped natural frequency. If you square it, omega d square is equal to omega n square into bracket 1 minus zeta square. So indirectly I have got this equation, this expression in this form. Now I'll substitute in this equation. Now C of s equal to 1 by s plus 2 zeta omega n divided by s plus zeta omega n whole square plus omega d square. Correct? Now you see the formulas. So in this case, if I want to apply this formula, then the denominator is right, but in the numerator s plus a. Here a is zeta omega n, here s plus zeta omega n, so that I need s plus zeta omega n. So that now I will slightly modify s plus zeta omega n plus what I will write? Zeta omega n. So now s plus zeta omega n whole square plus omega d square, s plus zeta omega n whole square plus omega d square. Is it right? Now this exactly this is you can correlate with this formula. But what about this? I want to apply this formula here, omega omega, here omega d is required. Here no omega d. What I'll do? I'll divide and multiply by omega d. The last adjustment is s plus zeta omega n divided by s plus zeta omega n whole square plus omega d whole square plus omega divided by omega d and multiply by omega d. Here this is what now standardized. So now I can apply this formula. This is a constant. The zeta is constant, omega n is constant, and omega d is constant. Now you can taking what? Laplace inverse. Taking Laplace inverse. Taking Laplace inverse. Now if I take a Laplace inverse of C of s becomes C of t, Laplace inverse of 1 by s becomes 1, because we know that Laplace of 1 is equal to 1 by s and Laplace inverse of 1 by s is 1. So next minus here. So this is the related to what? Cos. This is related to cos. So now s plus a, e raised to minus et, e raised to a is here what? This a is nothing but zeta omega n t. So e raised to zeta omega n, that is a into t cos of omega dt, because here omega, so here omega dt plus zeta omega n divided by, what is the omega d? Omega n root of 1 minus zeta square. I know omega d equal to omega n root of 1 minus zeta square. Now I will take a Laplace inverse by using this formula, that is sine e raised to minus at. Now a is minus zeta omega n, t sine of omega means here omega dt, here omega means here dt. Now I took the inverse Laplace. This is a time response of second order system now, but I will simplify this. One more step I will simplify. Okay. So now because here cos and sine, I will convert it into sine. Okay. I know that I'll take a common 1 minus e raised to zeta omega n t, as well as I'll take a LCM, then I'll take outside, I'll take LCM, then I'll take outside. Okay. So root of 1 minus zeta square cos of omega dt plus zeta, okay, zeta sine of omega dt. So how to convert the sine and cos into sine? Here sine a cos b plus cos a sine b is equal to what? Sine a plus b. Is that right? Correct. So I'll convert this is into sine a, this is into cos. How to convert this is into sine? Zeta is a constant. Say this is underdamping case, so that zeta may be 0.5, 0.6, 0.7. So if you put let us example 0.7, you will get this is a one constant, this is a one constant. But in the trigonometry I need a right angle triangle. In the trigonometry I need a right angle triangle. It should be sine, it should be cos. Sine means what? It should be what? It should be opposite side. Then only I will get a sine. I need here cos means definitely I will go for this, and this is a 90. By Pythagoras theorem I will find a diagonal root of 1 minus zeta square plus zeta square, so I will get 1. Now suppose say you take a theta or phi, suppose I will take a phi or it may be theta. Now sine phi equal to 1 minus zeta square divided by 1, otherwise root of 1 minus zeta square is equal to sine phi. And here I will take a cos phi is equal to base divided by hypotenuse. So now zeta is equal to cos. But what is a phi? Phi is equal to what? Tan phi is equal to opposite side by base, that is phi is equal to, this is very important, tan inverse. If you know the zeta you can find the phi, but phi should be in radians. So multiply by pi by 180 radians. So you should remember this important formula. So what are the important formula? You know zeta and omega n. Zeta and omega n are given. So you can find from zeta and omega n, there is a omega d, damped natural frequency. Then you find a phi. Phi equal to what? Tan inverse of root of 1 minus zeta square divided by zeta into pi by 180 what? Radians. These two are a very important formula. So now I will substitute this value and this value. This value and this value. Both the values I have to substitute. So now that is C of t equal to 1 minus e raised to zeta omega n t divided by root of 1 minus zeta square. So this becomes sine phi, and this already this is a cos. plus zeta becomes what? Cos phi and sine. Now this becomes what? Sin A cos B plus cos A sin B is equal to what? Sin A plus B. So now C of t is equal to e raised to minus zeta omega n t divided by root of 1 minus zeta square sin A plus B. A plus B. A, okay, I can take A, anyone A plus B. So this is the final time response of second order system. I write here time response of second order system under unit step input for under damping. Okay, here zeta and omega are given. Why you got a sine? Because in the previous class we have seen for under damping the poles are where the poles are for under damping the poles are S1 and S2 here. The complex S1 and S2. In the previous class we have seen the S1 and S2 are, I can write in the S1 value for under damping is minus zeta omega n plus omega d j and minus zeta omega n minus b omega j. Due to complex part for under damping the poles are negative real with complex we have seen in the previous class. Due to the complex poles I have got a sine. Sine means what? The system starts for oscillating. Okay, so due to complex part I have got a sine, but luckily I have a e raised to minus zeta. Zeta is opposition and minus, so it reduces the amplitude. So we will see in the graph. We will see in the graph. This is the final time response of second order system. If you see the graph, you take a spring mass system. Suppose this is a spring mass system. Mass, spring, damper, coefficient of damping C, stiffness of the spring K. Now you pull this mass for a certain displacement. Now what happened? This is a mean position. It starts from here. If you pull this, leave it, it goes above, it come down, it goes above, come down, then it will come to rest. Why it will come to rest? Because the damper is removing the energy in the form of heat to the atmosphere. That is a zeta. So e raised to, this is what in logarithmic decrement, that is e raised to minus zeta omega n t. So zeta is reducing the amplitude. Zeta is reducing the amplitude. And why you got a sine? Because the poles are negative real with complex due to complex part for a under damping. This is a case for what? Under damping. And this is a t is the x of t is output, t is the time in second. Now this output is, I can in general I can write c of t. So this is the graph for under damping. Initially our oscillations no problem, and after a certain period, that is called transient period, this is called steady state phase. Steady state phase, and this is called transient phase. Transient phase may be what, 10 second, 20 second, 30 second, maximum is 1 minute. After this the system will come to rest. So this is the very typical equation. It's called time response of second order system for unit step input. Suppose if it's a different, suppose step input with some magnitude, then just you multiply by a into bracket 1 minus e raised to zeta omega n t divided by root of 1 minus zeta square sine of phi plus omega dt. If suppose instead of unit step step input with a magnitude of 10, just you multiply it, then the same equation you have to multiply. A is the what? A step with the some magnitude. It is a unit step. Here in this case A is equal to 1. Okay, this is the 90% of our systems are what? Under damping. I hope you understood the what? The time response of second order system. The final equation you learned, graph you learned, what is the transient system you learned, what is the steady state system you have learned. Okay. And here you have learned what is the omega d equal to omega n root of 1 minus zeta square, and phi equal to tan inverse of root of 1 minus zeta square divided by zeta into pi by 180. In the next lecture, we will see the time response specification of second order system. We will start from this equation with this graph, and we will see some more time response specifications like rise time, peak time, and peak overshoot, and settling time. We will see in the next class. Okay, thank you.